first two. And welcome everyone to the HAO colloquium. Our today's speaker is Mariana Korsos from Aberystwyth University, UK. Mariana started her research career as an observing assistant at Degersin Heliophysical Observatory in Hungary. She moved to the UK when she had embarked after a very short 6-month period of research assistant post on her PhD studies at Sheffield in 2015. After completing her PhD degree, she received her postdoc position at the University of Sheffield. Next, she started her new and more substantive postdoc position at Aberystwyth University. Over the past few years, she worked on developing a new and novel solar flare prediction method. So today we will hear from her about solar flare prediction using magnetic field diagnostics above the photosphere. To Mariana now.
So thank you very much for the organizer for the opportunity to give this presentation. I'm glad to be here. So during this presentation, I would like to give an overview about what we have done so far in this research direction. But first of all, I would like to express and give a special thanks to all of my collaborators, because without them, I wouldn't have a material to present today. So I think everyone knows there are many kinds of eruptions on the sun, but from these, the solar flares and the CMEs are the most gigantic energetic explosion. And the flares and the CMEs often accompany with each other, but not always. And the problem is the most intense solar eruption have sometimes a strong effect on our space-based and also the ground-based facilities. And because of this, we try to predict them, because, for example, the solar flares, and actually the large energetic particles from the solar flares can reach the Earth within 20 minutes up to several hours and threatening the electronics of the spacecraft and the satellites. While the CME can reach the Earth within 1 day up to 4 days, depending on the initial speed of the CME or also the deceleration of them. But the problem is when the CME is colliding with the Earth's atmosphere and could set up a geomagnetic storm. And the result of this geomagnetic storm could have additional dramatic consequences for the number of ground-based and the space-based infrastructure. And nowadays we are more relying on developed techniques which are sensitive of these space weather events. So that's why we need to monitor the space weather continuously. There are many satellites doing this and also many ground-based telescopes. However, I would say there is 3 key missions that have helped the scientists to understand most the space weather events. The first one is the geostationary operational environment satellite. And some of these satellites are specifically measuring the flare intensity, how long does it take, and what was the position on the sun, which was the source region. And the second satellite, which was a kind of groundbreaking mission that allowed to us to monitor the solar activity that could affect the Earth. And actually, this SOHO has lasted far beyond on the initial planned 2-year mission. That's why the scientists work hard to come up with the improved replacement for the vital instrument on the board, and that's how the SDO satellite born. And this satellite was launched in 2010, and now unfortunately this is also getting older, and that's why the Solar Orbiter was launched just 2 years ago. And actually, they just started to release the observational data for the public. So that's why we're still just learning how to use the Solar Orbiter data. So I would say recently, if we would like to develop a new flare prediction method, we're still using these observations. Especially we are focusing on the solar observation and especially for the active region, which are the source of the solar flares. And we try to extract different features of the active region from the solar images that have some interpretable physical meaning. And after we try to find a relationship between the evolution of these extracted parameter of the active region and the flare activity. One of the options is to use the Montville system, which is based on the configuration and the characteristic of the positive and the negative polarities. And each group is labeled with a combination of the designation nature of the sunspot. And also we know that if the active region get a gamma and delta letter, it means that this active region will produce or could be produce a large energetic solar reactions. And also based on statistical analysis, we also know that if an active region producing a large energetic flares, then it's very often accompanied with the fast EME eruptions. The Montville classification is kind of useful to indicate which active region has a capability to produce large energetic explosion in the near future. However, further quantities are needed of the active region, which allows the physical comparison and the deeper understanding of the actual causes of the solar eruptions. And these parameters are scaled proportionally with the involved fundamental physical quantities, which are responsible for the flare and the CME eruptions. Recently, in the literature, we have more than 200 flare predictors. But do we know which we have to use, which one is the most accurate one, and etc.? This is a hard question, so that's why a group of researchers started a new project, which name was Flarecast project, and they collected almost all available predictors, and they tested their flare prediction capabilities by different machine learning techniques. And in this Flarecast project, our forecast parameter was also tested. And they said one of our parameters come up as one of the best parameters. And here I would like to show these parameters. This parameter was called as the sum of the horizontal magnetic gradient. So basically with this parameter, we are calculating the horizontal magnetic gradient between each opposite polarity sunspot pairs within an active region, and after we add together. So when the actual value of this parameter getting smaller and smaller, it means that the two opposite polarity of the active region are nicely separated. So it means that this type of active region are not so magnetically complex. Why? If this value is getting larger and larger, it also means that these parameters are, so the two opposite polarity basically getting more mixed. So it means that the magnetic configuration of the active region is getting more complex, and because of this, it can produce a larger energetic solar eruptions. And based on the forecast project, we were inspired as could we improve the flare prediction capability of this parameter if we combining with one of our parameters, which came up as a kind of mid-range parameter. So, and this parameter, what we choose, so-called the separation parameter. This parameter is a little bit more simple compared to this. So first of all, in the upper part of the equation is the distance parameter between the area weighted center of the positive and the negative polarity, while the lower part of the equation, so we are dividing this parameter with the diameter of that hypothetical circle what we can draw around the active region. So, and with this parameter, what we can measure, so if the value of this parameter is getting smaller and smaller, it means that the two opposite polarity is getting close to each other, and maybe it has some internal magnetic polarity mix part. However, if this parameter is getting larger and larger, it means that the two opposite polarity are far away from each other, and this also means that the magnetic field structure is more simple. So to test the joint flare prediction capability of these two parameters, we use logistic regression machine learning method. We chose the logistic regression because this is one of the simplest and widely used machine learning algorithm for the two-class classification. In our case, we have two classes. Do we have a large flare or we don't have a large flare? And also we voted for the logistic regression because it also predicts the probability of the occurrence of the binary event utilizing the logit function. So what we did, basically, we analyzed almost two solar cycle data. So we had more than 1,000 active regions. And each active region cases, we selected the largest intensity flare, which was produced by the active region. So in this case, we have one flare event, which is corresponding to one active region. And after that, we used the onset time of the flare as a reference time, and we calculated these two parameters of each active regions 24 hours, 18 hours, 12 hours, and 6 hours before the flare occurrence. And in this case, we have these 4 time interval is our prediction window. And after for each issuing time interval, we randomly extracted the 2/3 of the data as a training set, and the 1/3 of the data went to the test set. And based on this, in this manner, we don't have an overlap between the training and the testing set. So it means that one active region is relating to the training set or a testing set. And basically, this is one of the key roles during the machine learning. The training and the testing set cannot share the same data. So after we started the training process, we set up 2 models. The first model is a kind of very simple one where we just take into account the actual value of the 2 parameters before each issuing time, and also the intensity of the flare, which was hosted by the active region. And in the second model, we are a little bit were more strict. For example, we classified different threshold level because we wanted to see, can we increase the joint flare prediction capabilities if we are identifying different threshold level, and we try to find the most better one. So after when we trained our 2 models, after that we tested their prediction capability on the test set. And here I would like to emphasize that unfortunately the space weather and also within the space weather, the solar flare prediction is affected by the strong cluster imbalances, which means that we have far more negative example than positive one. That's why we have to apply different metrics to classify and also validate the prediction capability of our models. For example, in that case, we used 7 parameters, and by the forecast project, some of the horizontal magnetic gradient was shown to be the prediction capability is about 70% accurate, which is not so bad. So based on the testing set, we found that based on these 2 models, basically we could increase a little bit the accuracy with few extra percentage. And based on the accuracy, I would say the first model performs better compared to the second model. However, we cannot use only just one parameter. We also need to take into account more metrics, and especially that metrics which have take into account the strong class imbalances also. These are kind of weighted parameters, and based on this, the second model performs much better compared to the first model. So basically, with this study, we just gain an information about if we are combining different parameters which are good predictors, then we could increase the accuracy of the model. And also, if we are identifying a threshold, which is a kind of well-defined, then even in this case, we even can increase the prediction capability of this model. So after that, we had seen that basically the horizontal magnetic gradient is a good approach. So that's why we was thinking about what happened if we modify this parameter a little bit and we are just focusing on that area of the active region where the most of the large solar eruption coming from. And this part of the active region is the so-called delta spot. In the delta spot, we know the positive and the negative polarities are shrink within one penumbra, and here the horizontal gradient is so high. So that's why with this weighted horizontal magnetic gradient, we just focusing on the evolution of the delta spot. So first of all, we are calculating the total unsigned magnetic flux within the delta spot. And after we divide this unsigned magnetic flux with the distance between the area-weighted center of the positive and the negative spot. And after that, we calculate these three parameters at every moment of time. And when we started to analyze their evolution before the flares, we found two preferred behavior. One is from the weighted GM parameter, and the other one was the distance parameter. So this upper panel showing the evolution of this weighted GM parameter before the flare occurrences. The flare, the onset time of the investigated flare is highlighted with these blue lines, blue vertical lines. And what we found that this weighted GM parameter starts to increase, has a maximum value, and after started to decrease. And the flare always happened on after the maximum. Why in the distance parameter, first of all, the distance parameter started to decrease, reached a kind of minimum value, and after it started to increase again, and coming back about the same level where this decreasing phase started. And this about means that sometimes it has a 10% differences. And the flares usually occurred just after when this distance parameter come back about the same value. So we analyze more than 100 data spot, and in all the cases we found these two preferred behavior before the flare occurrences. And that's why we started to investigate, can we found some relationship between, for example, the maximum value of the weighted GM and the largest intensity flare which occurred after the maximum. So on the x-axis, we can see the maximum value of the weighted GM, what was measured, and on the y-axis, we can see the largest intensity which happened after the maximum. And we found this logarithmic function. So basically, we always had seen that all the flare happened after the maximum. So that means that when we can see that the weighted GM starts to decrease, then we have already have the maximum value. So from that, we could maybe we could give an estimation about the expected flare intensity, which can be happen after this decreasing phase. While in the distance cases, we also found a relationship between the elapsed time of the decreasing phase, and which is on the x-axis, and the elapsed time from the minimum point until the first flare occurrences, which is on the y-axis. And we found this linear relationship. So again, if we can see that the distance parameter starts to increase again, then we already have this time interval, so we could make a kind of prediction about when could be the first flare occur after when this distance parameter coming back about the same value when the decreasing started. So this WGM method was only just applied within the data spot. So after that, we started to wondering why we are applying different flare prediction method at the photospheric level. But actually, the flares not occurring at the photosphere, they are occurring somewhere in the lower solar atmosphere, and each model always shows that the magnetic reconnection is happening in the lower solar atmosphere. So that's why we met one of our colleagues, Pierre Chatterjee, who actually gave a presentation about her simulation. In her simulation, she simulated a delta type active region which produced a series of flares. And actually, we asked her, can we ask her simulation data, because we would like to apply our WGM method as a function of height. So we applied this WGM method from the photosphere up to 8 megameters. And from the simulation, we know that when the flare occurred. And first of all, we started to follow the evolution of the WGM parameter and the distance parameter at the photospheric level. And after that, we analyzed every 100 kilometers. And we found that in each flare cases, we could identify the two preferred behavior together between a certain height range. For example, we could identify the two preferred behavior before the B1 flare between the photosphere and 700 kilometers, while in the first C-class flare cases, we could identify the two preferred behavior just above 1000 kilometers. For example, in this plot is made at 600 kilometers above the photosphere, and you can see that, for example, we cannot see the full U shape of the distance, the preferred behavior of this distance. We just can start to identify this U shape above 1000 kilometers, and next to it this inverted V shape of the WGM parameter. And for example, in the B2 flare cases, we could identify the two preferred behavior together between 400 kilometers and 700 kilometers. And in the C2 class flare cases, we could identify the two preferred behavior up to 300 kilometers and 1600 kilometers. And also we found that sometimes this decreasing phase started earlier and finished earlier at a certain height. So that's why we created this plot. So in this plot, we have seen, so we are highlighting with these black vertical lines when the flare occurred in the simulation. The green dots are representing when the distance started to decrease. The blue line indicates when reached the minimum distance. And we can see that these, in all the active region cases, the decreasing phase started earlier and finished earlier at a certain height range. And even after that, we made a prediction of the expected flare onset time, which is shown by this magenta color. So for that, we use this time interval. And actually, these estimated onset time of the flare was well agreement on that part, on that atmospheric height, where actually the approaching started earlier and finished earlier. And we call this type of height range as an optimum height because if we could identify a preferred behavior earlier, then it means that we also can make a prediction earlier compared to, for example, to the photospheric part. And also we was kind of curious about why these starts earlier and finish earlier. That's why in the simulation we could calculate the ohmic heating of the current carrying field lines as a function of height, and we found that just before the flare, this ohmic heating has a kind of maximum value at a certain height range, and this maximum value is highlighted with this gray area. And if you look at it, actually the predicted onset time is well agreement on that height where actually this approaching started and finished earlier, and this ohmic heating maximum area also overlap with this area. So it means that maybe where these approaching start earlier and finish earlier, this could be also that height range where the magnetic reconnection happened in the simulation. So this result was kind of inspiring, and we was curious about what about if we using this approach on an observational data. However, we don't have a routine magnetic field observation through the solar atmosphere. That's why we need to use kind of mathematical tools to create the 3D magnetic field. And to do that, we could use potential field, linear force extrapolation, or nonlinear force extrapolation. So for our study, we choose the potential field extrapolation and the nonlinear force extrapolation. We choose the potential field because it is a quick method, and for the flare prediction purpose, we need to find quick methods. And we chose the nonlinear force extrapolation because it's theoretically it's give a more realistic picture about which is close to the reality. However, here I would like to highlight that during our parameter, we are not interested about the free energy of the system. So that's why the potential field extrapolation and the nonlinear force field extrapolation in that point of view playing the same role. So basically we want to capture some morphological parameter and to see how is it changing, developing before the flare occurrences. So we extrapolated the magnetic field with potential and also with nonlinear force field extrapolation of an active region at every moment of time. And after that, we have a different magnetic field map at the different height if we are making a crosscut. So we could apply this WGM method at the photospheric level, 300 kilometers above the photosphere, and etc. So this is what we did. Basically, we did the same analysis what I showed before in the simulation. And just to show an example, so this active region produced one X-class flare. Actually, this active region produced the first X-class flare from the last solar cycle, or actually the previous solar cycle. And this active region has two data spots. So we applied the WGM method in the first data spot and also in the second data spot. So the WGM analysis within the first data spot can be seen in this left-hand side. And here, basically, we cannot see the two preferred behavior of the two parameters before the flare occurrences. However, in the second data spot, we could identify the two preferred behavior before the flare occurrences. And actually, it is observational proven that the X-class flare is coming from this data spot. So from that point, I am just showing the analysis of this second data spot. So on the left-hand side, there is the analysis based on the potential field data, and on the right-hand side, we can see on the analysis on the nonlinear force field extrapolation data. And at the moment, we are 360 kilometers above the photosphere. And in both of the cases, we can identify the two preferred behavior. And actually, the unsigned magnetic fluxes within the delta spot, we couldn't identify any typical preferred behavior. So if we go even higher up, now we are at the 1,400 kilometers above the photosphere, we still can identify the two preferred behavior based on the two extrapolation data. And similar to the simulation, when we did this analysis as a function of height, we found that the decreasing phase of the distance parameter starts earlier and finish earlier at a certain height. And we did the same plot, what I showed, but it is a little bit more simple one. So what we can see here, this green color showing when the distance started to decrease. The blue color is representing when reached the minimum point, and this red one is showing when the investigated flare occurred. And the simple line showing the analysis, which is based on the potential field, and the dashed line is corresponding to the nonlinear force field data. And this plot is corresponding the first two column of these two plots on the right-hand side. So what we can see here, basically, in this active region cases, we found that with the potential field, the decreasing phase finished around 2 hours earlier on the 1,400 kilometer, which is something here. So, but in the nonlinear force field extrapolation cases, the distance reached the minimum distance around 40 minutes earlier compared to the photosphere, and this height was around 800 kilometers, so it's below around 1,000 kilometers. And from that, I would say the advanced prediction time, what I would say we could make a prediction in the potential field cases 2 hours earlier, but in the nonlinear force extrapolation cases, we could do 40 minutes earlier the prediction, especially to estimate the expected flare onset time earlier if we are applying them somewhere above the photosphere. And we also did this analysis in additional 3 active region cases, and we found that the optimum height was kind of much higher in the potential field cases than compared to the nonlinear analysis, but the advanced prediction time was almost the same. So that's why we decided we are using the potential field extrapolation in further cases, because the nonlinear force extrapolation, it took us a couple of months for one active region. And based on these, for example, it looks like for us it kind of doesn't matter which one is used, but if we would like to find a quick method, that means the best if we are using potential field extrapolation. And we analyzed, I think, 14 active region cases which produce X-class flare in the last solar cycle. And in all the active region cases, we found that this decreasing phase reached the minimum point a couple of hours earlier at a certain atmospheric height compared to the photospheric level. And actually, if this optimum height, if it was between 1,000 and up to 1,800 kilometers, then the advanced prediction time was around between 2 to 8 hours. And we say this height range could be a kind of optimum height, because if the optimum height was between this height range, then the estimated flare onset time was well agreement with the actual occurrence time, and also the estimated flare intensity was well agreement with the actual measured flare intensity. However, if the optimum height was below 1000, in that case, the estimated flare intensity was not well agreement with the actual measured one. So, and after that result, we was curious about what happened if we are studying another parameter, for example, the magnetic helicity as a function of height. So recently we are working with the helicity, and especially we are focusing the evolution of the emerging helicity flux term and also the shearing helicity flux term. So these two helicity flux term is calculated based on this equation, which was introduced by Mitch Berger. And when we are studying the evolution of these helicity flux component in a flaring cases, we found that the two helicity flux component, the emerging one and the shearing one, has a common period before the flare occurrences. However, in the non-flaring active region cases, we found that the emerging helicity flux component has a different periodic, have a different period compared to the shearing one. So it's a kind of interesting oscillatory behavior differences between the flaring and the non-flaring one. And also we decided we extend the application of this helicity flux at different heights, what we did with the WGM method. So again, we are calculated the helicity flux component at every 360 kilometer height from the photosphere up to 4,000 kilometer. And we found that in the flaring active region cases, the identified largest period of the emerging and the shearing one, and also the total helicity flux, which is actually coming from the two helicity flux component if we are adding them together. We found that the largest period of the three helicity flux component at the photosphere remaining the largest, and the common and also the common period of this three helicity flux component from the photosphere up to some height. So for example, in this first active region cases, this 18-hour period remaining the largest and the common period from the photosphere up to 1,500 kilometers. But in the non-flaring active region cases, we found that the largest period of the emerging helicity flux component is different compared to the shearing one and the total one. And during the analysis, we found that somehow the shearing helicity flux component contribute more to the total helicity flux. But basically, based on this model, we can say that if the horizontal and the vertical component of the magnetic helicity became a so-called coupled oscillatory system from the photosphere up to some lower solar atmospheric height, for example, the chromosphere or until the lower corona, then this active region has a capability to produce a large energetic solar eruptions. And we also, when we did this analysis, we was surprised because these periods, these common periods, actually appeared again a little bit earlier at a certain height compared to the photospheric counterpart. And to study these periodicity, we identify the local maxima of these identified period, and we plotted them as a function of height. And here you can see again basically the identified local maxima within the wavelet analysis. these are changing as a function of height, and at some atmospheric height, we can identify earlier compared to the photosphere. And based on these larger sample analysis, we also found that these local maxima appearing around 2 to 8 hours earlier, between 700 up to 1,500 kilometers compared to the photosphere. And this earliest appearance of the precursors with the magnetic helicity is comparable with what we identified with the WGM method, and also the atmospheric height range. So at the moment, two parameters showing us there is some optimum height range in the lower solar atmosphere where we could identify so-called precursors of each parameters 2 to 8 hours earlier. But to make a more firm conclusion, we started to analyze more flare predictors as a function of height, and a couple of students are working on this recently. And another aspect of this study, now we have developed a kind of new telescope which is based on the magneto-optical filter, and this instrument was developed in the UK, and now we are taking it to Hungary, and in the next months it will be set it up, and from June, basically the students will start to use this telescope. So this telescope can measure the magnetic field at some atmospheric height. And we hope that with this routine magnetic field measurement in the lower solar atmosphere, we can use this magnetic field measurement to increase the flare prediction capabilities with different parameters. Or if we also can use these additional magnetic field measurement to further improve the magnetic field extrapolation, because if we are using more boundary condition, then in this case we can make the extrapolation techniques more accurate. So thank you very much. And if you have any question, I am happy to answer, or even comments are also welcome.
Thank you, Mariana. So we open the room for questions. So either anyone has a question, either just, yeah, Matthias.
Yeah, hello. Thank you for the very interesting talk. So I have a question. What does it mean physically that you can improve the flare prediction by using this potential field extrapolation and looking at field at a greater height? I mean, the potential field doesn't really add new information to the problem, since it's completely determined by what is in the photosphere. But I kind of think about is, I mean, in some sense, the potential field extrapolation is simply a smoothing operation with an exponential kernel in Fourier space. So is it that your method, when you apply to the photosphere, gets kind of, I mean, confused by a lot of the small scale structure which is present in the photosphere, since that kind of relates to magnetic field, which closes down and doesn't reach high up into the corona? And applying the potential field, you essentially apply a smoothing operation to the photosphere and focus more on the larger scale structure and the arrangement of the larger scale structure.
That's true, and actually that we are focusing larger structure, so we are not focusing these small changes. So with these prediction parameters, we try to catch some general changes within the magnetic field. And as I said before, basically we are not interested about the free energy of the system. We just want to see some morphological properties, these morphological properties can be identified on a larger scale. Yeah, you are right. So the potential field is a kind of very basic approach, and it's smoothing the magnetic field structure, but still, based on our analysis, it somehow it was found that the preferred behavior can be identified earlier of these two parameters. And it means that if we could identify this preferred behavior earlier, which we are using to estimate the expected, so basically we are using these preferred behavior of the parameter to predict flares. And it means that if we could identify earlier, even with just a couple of hours, that it means that we could make the prediction earlier compared to the photospheric one. And actually, this is one of the biggest questions in the space weather, how we could increase the prediction window, even with just a couple of hours extra, but the goal is to predict 3 days earlier, but I think it is kind of still far away, but every extra gain hour with the prediction, it's a kind of a bigger step. So I don't know, actually, honestly, I don't know why we are observing these flare prediction, so these parameters earlier at some height, but it should be somehow relating that the flares are not occurring at the photosphere, they are occurring somewhere in the lower solar atmosphere. And these extrapolation should give some closer picture about how the magnetic fields are developing in the lower solar atmosphere. And actually, if I am showing this picture, here. From that, actually here we can see an observation, and here is the potential field and the nonlinear force extrapolation. And from that, to be honest, I cannot really decide which one is the more accurate one. So I think this is a kind of very not really properly answered question, which one is the give the more realistic distribution of the magnetic field lines within an active regions. But actually, if we would like to study the free energy of the system and etc., definitely we should use the nonlinear force extrapolation.
Any other question? Anyone has a question can jump in and just speak out. So in the meantime, I have a question related to what Matthias was asking. If you go to the slide 23, just 2 slides, yeah. No, not that one, maybe the next one. Yes, you were talking about pre-flare properties, and looks like you see the better pre-flare properties in NLFFF compared to PF.
Yes.
And on the other hand, I'm a little confused that you see better pre-flare properties in NLFFF. On the other hand, your PF calculation is predicting the flare onset 2 hours before, and this one NLFFF only 40 minutes before. So, so these can you clarify a little bit?
So here we plotted a kind of best polynomial fit, and after we identified the maximum and the minimum value, and at every height, and after that we plotted these values of the maximum and the minimum. And when we plotted, we had seen that these values are changing as a function of height. Maybe that was not the best visualization of it, but so for example, here in the potential field cases, these green represent to that point because we are using this time interval for the flare prediction, and these blue dots are representing with these lines. And as you can see, it is not a straight line, basically. It has some little jumps. And from that point of view, because we are using these time intervals, we are going back these time intervals to estimate the expected flare onset time. And if it is started earlier and also finished earlier, then it means that if it is finished earlier, then from this time interval, we could make a prediction to estimate the expected flare onset time earlier, because at some height this is finished earlier, so we could get this time interval earlier compared to the photosphere. But in the nonlinear force extrapolation, this changing not as big compared to the potential field.
Okay. Other questions? So, does anyone have any other question?
This is Philip Judge. Thanks for the talk. I wasn't able to follow all of it. I had to step out for a bit. So this is admirable work. It's very interesting to see, the parameters coming up that you're looking at. Do you think that this constitutes evidence that flares are intrinsically predictable things, as opposed to, say, something like a lightning strike, where you gradually and very slowly build up energy, but then you release, at some random point later on, something which is intrinsically not really predictable? Do you think that the forcing that's going on here is directly evidence that a mechanical kind of cause and effect thing from the photosphere really is going to work?
So if I correctly understand, I would say because these magnetic fields are coming from the solar interior, and based on the helicity, when it's oscillated from the photosphere up to some height with the same period, it means that, of course, the photospheric motion so the photospheric motion is causing something which is causing the magnetic reconnection. So, but when we are going up, somehow these parameters, I don't know, somehow showing that they could predict these events earlier compared to the photospheric one. But I am sure because, and also the reconnection, so the physical parameters are changing dramatically from the photosphere and even the chromosphere and up to the corona. So what does it mean exactly? I would say I don't know, but something is jumping. We already know that the chromosphere has a different, the temperature and everything is changing so quickly from the photosphere to the corona. So why in this case these parameters do not have a other behavior, or they can predict the flares much earlier compared to the photosphere. So too many things changing in this short height.
Okay, so I guess it's a silly question, really, because it's a question of degree. So I think these are unpredictable on timescales of seconds, but nobody would claim that they are, right? But
yes.
But what you're seeking is a mechanical connection between the photosphere and then the middle chromosphere, and you found that the chromosphere is more effective at predicting things, and so I think I've always been fairly dubious of flare prediction research, but I think if you've defined a problem rather nicely, and you've shown something that is predictable, and that is that there are parameters that you can find which, if they were just random events, you wouldn't get the results that you do, right? I guess that's
yes, you are right. The problem is these flare events happening very quickly, but we don't have these detailed measurements before the flares, because only just the techists now have this huge resolution, but we also have to be lucky to point out to these active regions, and we cannot process that amount of data, and for the flare prediction purpose, we need to catch that type of changes, evolutions of the active regions, which are more global, more general than these small scales.
Yeah, and then the natural next question for me is, can you do the same kind of training using models of erupting CMEs and things? Maybe you said something. As I said, I wasn't there for the whole talk. So, do you think this can be done effectively with training on models that do erupt, and then looking for similar looking signatures for CMEs at this point?
It should be, yeah. And there is another. So many researchers try to identify precursors for the CMEs, and actually the problem is we call them a confined flare when the CME just cannot erupt and leave the solar surface. And a couple of researchers try to understand why the CME couldn't erupt, and the other case it could erupt. So yeah, we're trying to go in a small details, but in generally to predict it, I think it's a kind of hard task.
Okay, thank you so much once again.
Thank you.
Any other question? I don't see any other questions, so let's thank our speaker for a nice talk and nice interactions.
Thank you very much. Bye.
Bye-bye.